Good morning to everyone. I'm Dr. Sumi MS. The topic of my today's presentation is Technology Scaling from Unit 1 Mass Transistor Principles. On completion, the students will be able to understand the need for scaling and also categorize the types of scaling. Technology scaling. In VLSI design, the transistor size has reduced by 30% for every 2 to 3 years, and the scaling is the concept of reducing the feature size of the transistors. Nowadays, transistors are becoming much smaller, and at the same time their switching speed is getting increased, being cheaper and also having lesser power dissipation. Designers need to predict the effect of feature size scaling on chip performance to plan future products and ensure existing products for getting reduction in cost. Transistor scaling. Dennard's scaling law predicts that the basic operational characteristics of a MOS transistor can be preserved, and at the same time the performance can also be improved. Certain parameters are being scaled with a dimensionless factor S, and these parameters include the following: all the dimensions of the transistors in X, Y, Z directions, the device voltages as well as the doping concentration densities. Types of scaling. The first type is constant field scaling, or which is also called as full scaling. Magnitude of internal electric fields is kept constant, and here only we are scaling the dimensions, that is the lateral dimensions are being changed, and threshold voltage is also affected. So from the diagram we can compare the original device with the constant field scaled device, in which the lateral dimensions are being modified. In constant field scaling, the electric currents remain the same as both the voltage and distance are getting reduced, and 1 by S is the scaling factor that is being applied to all the dimensions of the device, and the voltages and the concentration densities. And the drain current per transistor are scaled by a factor 1 by S, and here the number of transistors per unit area is scaled by S square, and the current density is scaled by S, and power density here remains constant. So we shall see the consequences of constant field scaling, and various quantities with respect to the device are mentioned here, like channel length, channel width, gate oxide thickness, junction depth, power supply voltage, threshold voltage as well as doping densities, and their respective factors before and after scaling. So when the channel length is considered to be L before scaling, its after scaling value will be L by S, where S is the scaling factor. Similarly, if you are taking the junction depth as X suffix j, the new junction depth, that is the after scaling junction depth, is found to be Fxj by S. Power dissipation is reduced by a factor of S square, that is the original power dissipation, if it is considered to be as P, the after scaling power dissipation is given as P by S square. And similarly, the gate oxide capacitance is scaled as Cg by S, where Cg is the gate oxide capacitance before scaling and S is the scaling factor. As a whole, there is a overall performance improvement being noticed. Next comes the constant voltage scaling, where the supply voltage is held constant while the scaling process is carried out, and the constant voltage scaling, which is also called as a fixed scaling, offers a quadratic delay improvement as well as cost reduction. It is also maintaining continuity in the input-output voltage standards. The constant voltage scaling increases the electric fields in the device, and the drain current per transistor are scaled by a factor S. The number of transistors present in a given unit area is scaled by a factor S square, and the current density is scaled by a factor S cube as well as the power density by S cube. A 30% string with the Dennard scaling improves the clock frequency by 40%, and as a result there is a reduction in power consumption per gate by a factor of 2. Maintaining a constant field has the further benefit that many nonlinear factors and Biot mechanisms are being unaffected. But from 90 nanometer generation technology, the voltage scaling is getting slowed down due to the presence of leakage current. This may ultimately limit the CMOS scaling. Lateral scaling. Another approach to this is lateral scaling, in which only the gate length is getting scaled. This is commonly called as a gate string mechanism because it can be done easily by to an existing mask database for a design, and here only the length of the gate is being strung. The drains current IDS per transistor are scaled by a factor S, and the number of transistors per unit area is scaled by S. Current density and power density are getting scaled by a factor S square. The industry generally scales process generations with a 30% shrink, and this reduces the cost of a transistor as well as the area of a transistor by a factor of 2. A 5% gate shrink, which is obtained with a scaling factor of S equal to 1.05, is commonly applied as a process to boost the speed of the components in this process. So here we are given the parameters which are being scaled for different scaling methods, Dennard scaling, constant voltage as well as lateral scaling methods. So the length L can be scaled by a factor 1 by S for all the three types of scaling methods. Same way, width is considered to be scaled by a factor 1 by S for Dennard scaling and constant voltage scaling, whereas it is kept as such for lateral scaling. The interconnect wires are also subjected to scaling. So wires to be scaled equally in width and thickness to maintain an aspect ratio which is close to 1 to. Wires can be classified as local, semi-global as well as global. Local wires will be running within the functional units and use the bottom layers of the metal. Semi-global wires run across the larger blocks or cores. Typically, they are present using the middle layers of the metal. Both local as well as semi-global wires are scaled with a feature size, and global wires run across the entire chip using upper levels of the metal. Global wires do not scale with feature size. Indeed, they may get longer by a factor of DC or on an order of 1.1 because the die size has been increasing gradually. When the wire thickness is scaled, the capacitance per unit length remains constant. This is in the case of interconnecting scaling. Quiz questions on technology scaling. Distinguish between constant field and constant voltage scaling. Thank you.